Go.
This is slightly different than what I promised to talk about in the program. I'll talk about secretary problems and profit inequalities. And they both have a lot of applications to mechanism design. I don't really know what the applications are. Michal can tell you more about maybe in the next talk. But anyway, as a proof that they have many applications, I was asked by several people in this workshop to talk about this work, so hopefully it's useful, at least to some of you. And this is partly based in Jordan work, which is a hill thing on TV. So, secretary problems, you have n secretaries, which each one has some value. And you want to hire one of them, and they arrive online, but you have the advantage that they arrive at the random order. So that gives you something over the overall worst case thing. But the choice of secretary values are worst case. So the blue secretary arrives, you say, okay, no, 3 is maybe not enough. Green secretary arrives, 2 is not enough. And anyway, so they arrive online, and once you hire the secretary, you must decide immediately whether you want to hire the secretary or wait for a better secretary. So blue-green, we waited for a better secretary. The pink secretary arrives. You say, oh, 7 looks like a reasonable value, but you really made a mistake because you should have waited for the black secretary who's worth 100. So your goal is to maximize the probability of hiring the best possible secretary in hindsight. Questions? No, this is familiar, right? Okay. So another very famous online problem, slightly less famous, is the profit inequality. So now the order is worst case, but on each day the value is random and it's drawn independently from some known distribution. So day 1 we have a value drawn from D1, D2, etc. And the DIs are not necessarily identical, but we know in advance what they are. So on every day, do we take so on day 1 we saw x1 is 8. You can say, okay, do I take 8 or do I want to wait for a better value? And day 2, x2 was drawn from D2. It turned out to be 6. Maybe I know there's nothing better waiting for me, so I'll take the 6 even though I should have taken the 8 earlier. And again, so the goal is to maximize your expected profit, and it's called profit inequality with a PH, because you're competing against a prophet who knows in advance all the realizations.
Sorry, Aviad, in this model, I know which distribution corresponds to which day?
Yeah, so the days are fixed, and you know the distribution each day, but you're waiting for, so on each day you're participating in some gamble, you're going to the casino, you know on the first day you're going to play blackjack, on the second day you're going to play poker, etc. And you know your distribution over outcomes, but you don't know in advance the realizations.
So this is pretty easy to solve from backwards.
Yeah, so if all you wanted was an algorithm for this case, you can do a backward induction or a dynamic program, and you can figure out what's your value for the last day, and what's your expected value for the last day, and then you can say on day 3, am I better off, for each value, am I better off waiting or taking the value from the last day, etc. What we are interested in knowing here is how well this optimal algorithm can do in comparison with the optimal offline algorithm. So this is typically a competitive analysis. You're competing against the profit. More questions? Maybe later. Okay, so both of these problems are classic problems, and recently in algorithmic game theory, there's been interested in extensions of those problems. The most famous example is this matrix secretary problem, where again there are n secretaries that arrive in a random order, but now I have a matrix over the secretary. So you don't need to know what a matrix is for this talk. I don't really know what a matrix is. I can tell you this is a matrix. So at most one of the black and blue secretaries, and at most one of the pink and green secretaries. That's a matrix. And so the set of secretaries that your algorithm is allowed to pick has to be an independent set of the matroid, or a feasible set in this matroid. And your goal is to maximize your expected profit. And we can ask the same questions for a general feasibility constraint. So for example, if you want to do either some subset of the black and blue secretary, or a subset of the pink and green secretary, but you're not allowed to pick the blue and the pink secretaries. So this is not a matroid. This is a more general feasibility constraint. And you can ask the same question, pick a feasible set of secretaries, maximizing your expected profit. Again, you can ask this the same questions for profit inequality. So you have matroid over the gambles, and you want to maximize your expected profit. And again, the same analog for a general feasibility constraint. So that's the model, very simple. And here are some of the background results that I should tell you about so you can understand the new results. So classically, if you just have one secretary or you're only allowed to pick one gamble, then there is a constant factor competitive ratio. So you're doing up to a constant, you're doing as good as the offline algorithm with a profit. For the matroid secretary problem, there's been a very long line of work trying to resolve this, trying to get a constant ratio, constant competitive ratio. So there is a log R, then there's squared log R, then there's log R, and then there's log R with a better constant, and there are a bunch of special cases that are resolved. For the matroid profit inequality, there is a single paper that does a tight to competitive ratio. So, I don't know what are matroids, so I want to talk about general arbitrary feasibility constraint.
Is that downward closed?
In a second.
The work of limiting the approximation of E, it's the value of the second or the probability of getting the best one?
Okay, thanks. So this first one, it's the probability of getting the first one, but you can imagine that so you don't know what's the range. There is no range of the secretaries. So each secretary can be infinitely better than the ones. If a secretary is better than some secretaries, he's infinitely better than all of them, and it's almost the same as. It's not exactly the same. Essentially the same.
And the other results are cardinal, right? In the model.
Sorry.
And the other results were originally in the cardinal model of looking at the value or not the order.
Other results? You mean these results? Yeah. It's all you're computing the sum. Now you have a sum. You have a matrix. So you want to talk about the sum of the values of the secretaries. Okay. So it's no longer about getting the best secretary. So like Noam said, if you're talking about arbitrary constraint, it's not necessarily. It can be something like a constraint like you have to pick both of these secretaries. Okay. So it's not necessarily downward closed constraint. And if I have to pick two secretaries and I have no idea that the other secretary is going to come or when is the other secretary going to come, then it's essentially hopeless. And we can show almost linear upper and lower bounds on the competitive ratio. So the more, and arguably the more natural constraint is a downward closed constraint. So like at most 2 or at most 2. And here, if you want an efficient algorithm, then again, there's essentially nothing you can possibly do. Because, for example, if my set of feasible, my family of feasible secretaries I have a graph over the secretaries, and I'm looking for all the independent sets. So if you want, it's NP hard to do any approximation. But if you don't care about approximation, maybe there is some chance. But even if you don't care about computational efficiency, there is log n over log n lower bound on the competitive ratio. So we're not going to get a constant competitive ratio, but hopefully we can get very close to this log n. And so we hope to get very close, but let me mention that before, when we started working this, nothing sublinear was known, and we would have been at least somewhat happy even with n over log n. That would have been a big improvement over what was known. Okay, so so let me mention, so this lower bound holds even for 0, 1 valued. So even if each secretary or each gamma has a value that's either 0 or 1, and we get an nearly matching, so order of log n competitive ratio, and there's by the trivial reduction for general values, we lose a factor of log r.
What is r?
Sorry, so n is the number of secretaries. R for matrade is the rank of the matrade, or for general feasibility constraint, it's the size of the largest set. So in this lower bound, for example, R is logarithmic in n. Okay, so this is the result again, and it's tied up to this log factor and the factor of log r. And so we cannot expect the algorithms to be actually efficient in the standard sense, but if we have something like a demand oracle, so demand oracle says, I give you some set of secretaries, tell me what's the largest feasible set, what's the largest feasible subset. So if I have something similar to this, then these algorithms are also efficient. So that's the first result I want to tell you about. And let me tell you now about a second set of results. So far I told you I want to maximize the sum of the values. But I can also look at maximizing some function of the secretaries that I hire. For example, I want to have a submodular or subadditive function over the secretaries. I want to maximize this function. And otherwise, the settings stayed exactly the same. So there's been some previous work on this, and I was really jealous. I wanted to do some submodular profit inequalities. And if I'm talking about independent values, it's not even clear what does it mean to be subadditive over independent values. So I need to have a distribution. It's not what does it mean to be subadditive over independent distributions. So it's the right analog of this submodular secretary problem is to say that in each day, each gamble has k possible outcomes. So for example, on day 1, I draw tickets to some basketball game. On day 2, I might get a ticket to some soccer game. And now my valuation function is, say, subadditive over the subsets of tickets to all the games possible. And recently we've been using a similar approach to model what does it mean to have a buyer with subadditive but independent valuations over items. Questions about this new framework? Okay, so what can we prove in this new framework, in this the old submodular secretary? So recently there is for the submodular secretary, there is a nice reduction that almost preserves the approximation ratio to the additive secretary that we discussed in the previous slide. And if you can get a constant ratio for the matrade secretary problem, you also get it for the submodular matrade secretary problem. And recently, Moran Feldman and Rani, who's here, introduced a notion. They studied the secretary problem when the evaluation is slightly supermodular, But even so, and they get a competitive ratio that depends on the supermodular degree, how not submodular you are, and on log R. But even in this restricted complements setting, you need to know something about the future. Otherwise, you have no chance of doing anything with. Otherwise, you have no chance of getting the complement if you have no idea that complement is arriving. So, what can we say anything beyond submodular? Then sort of the next thing up is subadditive evaluations. And for subadditive, there's a root n lower bound for some restricted queries. And even if you look at the most general thing, the same log n over log n lower bound holds, even for both of these are even for cardinality constraints. So just the simplest constraint possible over the secretaries you're picking. And our result in the setting for the some modular profit inequality with majored constraint, we prove a constant competitive ratio. And for the subadditive with the downward closed constraint, so the most general setting, it's incomparable to the submodular degree, but otherwise it's the most general setting that's been considered, we can get a log n times log squared r. So polylog in r, and there's only the log n factor from the lower bound. Questions? Okay, so this is it. That's all these are all the results. Let me tell you a little bit about the techniques. So, okay, so there's 3 completely different algorithms that we somehow bunched into 2 papers. So the first one, or the last one, the submodular profit inequality. The techniques that go into this algorithm are something that's called an online contention resolution scheme. I can tell you about it offline, but and the other interesting ingredient which we have partly developed is called the correlation gap. So you want to look at the expected value of f of s, but where s is a random subset, and now you have 2 possible ways of drawing s. One is you draw each I is going to be an s independently with some marginal probability, and you compare that with the best correlated distribution with the same marginals. And we show that up to a constant factor, if f is a submodular function, possibly non-monotone, up to a constant factor, these are these are the same, even though the correlated could be much better in principle. So that's the first algorithm. Okay, we're done. The second algorithm is that's probably my favorite algorithm of all of those. It uses something that I call a dynamic potential function. I really love it. It's a little bit too complicated to explain in a talk, but if you catch me offline, I'll be happy to tell you more about it. The simplest algorithm is the one for this downward closed secretary, and I'll tell you more in the rest of the talk. Okay, so just reminder, the theorem that we want to prove a log n competitive ratio for the secretary problem. That's the secretaries arrive at a random order. Each secretary is either 0, 1. And yeah, we have some arbitrary downward closed constraint. Ready for the proof? Okay, so before I show you the proof, let me give you one piece of intuition. When the secretary arrives, so if it's 0, you can ignore him. If he's a 1 secretary, you want to know if he's a good secretary or bad secretary. And good or bad means how well the secretary interacts with the other secretaries. And for this, so you have no idea how well this secretary is going to interact with future secretaries, but you should look at your history, and if this secretary interacts well with the previous secretaries, because of the random order, you expect the secretary will also interact well with the future secretaries. So with this vague intuition, let me show you an algorithm. So the first step in most of those secretary problems is an exploration stage. We interview the first half of the secretaries, but you don't hire any of them. You just want to learn what the population looks like. And yeah, nice. So you can pick this best feasible set. So the pink, blue, and black secretaries are the best that you can do out of this, you could have done in hindsight, out of these first n/2 secretaries, but you did not hire any of them, right? And this is, of course, an expectation as good as half of the secretaries of opt of the total offline optimum. So the second stage is the exploitation stage. This is the more interesting stage. We're going to have a sliding window that shifts forward as we interview more secretaries. And every time we shift the sliding window to your right, we're going to lose the first secretary that we interview. So maybe we lose one. So our current value maybe goes down by 1. But maybe the next secretary that we interview is very good, and we can add him to our current set and get back a +1. N/2. So we have a sliding window of size n/2, and and every time I have to remove the I secretary, and I try to add the n/2 plus I secretary, if he adds to my current feasible set, so it's the offline optimum over anything before the overall everything before the is it red, the dashed line, and after the dashed line, it's I'm already committed to what I already picked. So maybe I don't like the green secretary, but now the best subset is black, blue, and pink. So I pick this new pink secretary, and now I'm committed to this pink secretary, etc. Yep. Mm-hmm. Okay, yeah, so here this is the subset I think I look at what I have now. This is what I would have done in hindsight. I don't actually pick them. I don't actually hire them. I just think, okay, this is a nice subset to have. Okay, and given what I have, what I already have, what I imagine I already have, this green secretary doesn't add anything, so I don't hire him. Yeah. Yeah, so this is the entire algorithm. Okay, so every time you look, does this new secretary add to your combined set of imagined secretaries that you imagine you would have hired and the secretaries you actually hired from the second half?
So if you shift in this shift, it's a secretary that was not hired, was not hypothetically hired, then you will certainly not add the new.
No. It's independent. So maybe I lose one, maybe I add one. It doesn't have to be the same. Okay, so the intuition is that the secretaries arrive in a random order. So, the I secretary and the n/2 plus I secretary, they should be the same. So I expect to lose as many ones as I add as many ones, right? So I expect to recover a constant fraction of opt. What's the catch? Right, so I lost this blue secretary, I got another blue secretary, so it's all good. And this is not just an expectation. I have a very good concentration. So if you take whatever fancy martingale concentration equality off the shelf that you want, you expect that the number of plus ones is approximately the same as the number of minus ones. What's the probability that they're very different? The best kind of concentration bound you can hope for will give you a probability that is 2 to the, it should be 2 to the minus number of minus ones. So 2 to the minus opt, approximately, where opt is the value of the offline solution. And there is a concentration inequality that gets you essentially that.
The number of 1 or minus 1 in the selected set.
So you run this algorithm, right? And at each step, you either you have a minus 1 because you lost this leftmost secretary is one that you liked, or you maybe gained a secretary. So maybe you have a plus 1. So the number of a priori the number of plus 1s and minus 1s should be about the same, and it's with a very high probability. The probability that they're very different looks like 2 to the minus opt. That's the probability of a large deviation. Okay. But once we already picked some of the secretaries on the right side, the minus 1s and plus 1s are not independent of what we already picked. So we have to condition on what we already picked, and it's a whole mess. But instead of that, you need to do just union bound over all the choices that your algorithm can possibly make. So if alg is the value of the algorithm, then in total you're making n choose alg choices, and we're just going to take a union bound over all of the choices the algorithm can possibly make. And this gets us back the independence that we need. So we have a union bound we have n choose alg, that's approximately n to the power of alg, times 2 to the minus opt. We want this probability to be less than 1, otherwise we didn't get anything. So we need alg to be approximately opt over log n, and that's the log n factor. And this may seem like a wasteful analysis, but this is an almost tight log n competitive ratio. So this is the entire algorithm n proof, and hopefully you have more questions. Yes, Amos. Okay, so the question was, will an algorithm like this give a constant ratio for the matrix secretary problem, which is this famous open problem I told you about earlier? And the answer is this has nothing to do with the matrix secretary problem, because this is only 0, 1 values. So I sort of ignored all the 0 secretaries and only looked at the 1 secretaries. Yeah, I mean, maybe, right? But all this algorithm and this analysis says nothing about the values of the secretaries, whereas in the matrix secretary problem, the 0, 1 case is trivial because you just pick a maximal independent set. And the interesting case is beating this log R factor that we just gave up and took, okay? So because of the different values, we lose a log R factor. In the matrix case, you can do some very, very clever tricks to get it down to log R and maybe constant.
I mean, I'm just saying that the same intuition here. If you took things.
Oh yeah, of course. This is definitely the intuition to any variant of the secretary problem. Is you should have an exploration stage where you typically don't hire any secretaries and you just learn what the population looks like, because otherwise you don't know anything. And then you assume this is roughly what the population looks like, and you try to optimize for the on the exploitation stage. The matrix secretary problem, it goes to very fine details about the properties of matroids, which, yeah, I'd be happy to know more about. More questions about the? Okay.
Thank you.
Yeah, it's okay.